Hi, I'm Messianic Michael, and we're working another physics problem that came in by request today. It says to calculate the average horsepower to raise a 200 kilogram drum a height of 50 meters in 3 minutes. And keep in mind we've changed the numbers a little bit so that the student can get some practice working the problem with their numbers at home. And let's also remember that all science and engineering can be understood in accordance with the biblical mandate to be fruitful and multiply, fill the earth and subdue it. So science empowers lots of engineering, medicine, agricultural advancements that are helpful for being fruitful and multiplying, filling the earth and subdue it. And keep in mind that God blessed them and said, so it's not just a mandate, it's a blessing and a fiat. So with the instruction that God gives, He also gives the ability to carry it out. So let's interpret this problem, and interpret is the first step of our idea problem solving format, our framework. Interpret, develop, evaluate, and assess. So to interpret, we want to recognize the general principle or principles of physics that are involved in solving this problem. So this problem involves the definition of horsepower, which also has to do with the definition of power in physics. And let's also think about drawing a picture here. So to draw a picture, we just start with a drum on the ground, and the drum is going to get raised from an initial height of 0 meters to a final height of 50 meters. The drum has a mass of 200 kilograms and is raised through this distance in a time of 3 minutes. And one step that we often need to take in physics problems is converting to the MKS system of units, meter, kilogram, seconds, or the SI system of units as it's also called. So we just do a quick unit conversion and convert the 3 minutes to 180 seconds. So we've got our interpretation of the problem, including the principles in a picture. So now let's move to the develop stage of our problem solving framework. And to develop, we want to articulate a bullet point plan for solving the problem. So convert units, which we've already done. We want to recall the formula for power. And there's some intermediate steps there. So to execute that, or to carry that out, the formula for power, we're going to have to also recall the work energy theorem, sometimes called the work energy principle. And we're going to use that to compute the work. Compute the work in lifting, and then the power is just the work over the time. And then once we compute the work, when we compute the power has units of watts, and then we need to convert the work from units of watts to units of horsepower, and we do that just by looking up the conversion factor. Okay. So let's go ahead and carry things out here. We converted our units already. We recalled the formula for power. It's the work done in a given time. And now we need to think about the work energy theorem. And there's some intermediate steps here. But the work energy theorem basically says if we call the work W, it's equal to the change in kinetic energy. So when positive work, and actually I erred there in calling it kinetic energy. It's kinetic energy in some systems where all the energy is kinetic. In this system, you've got both potential energy and kinetic energy going on. So in this case, the application of the work energy theorem is the total energy. So assuming it starts at rest and it ends at rest, the change in energy is all equal to the change in potential energy. So in this case, the work is equal to mg delta H, because as you recall, the potential energy of a system is mgh. The change in potential energy of the system is mg delta H, and since all the energy is potential, starts at rest, ends at rest, the work is equal to mg delta H. So now we can go ahead and compute the power. Let's give it the uppercase P. The power is going to be mg delta H over the time interval T. So the mass is 200 kilograms times 9.8 meters per second squared. And the delta H, squeeze it in there, run it out of room a little bit, but it's 50 meters. And then the time is 180 seconds. So let's just think a little bit about our units before we plug in the numbers. It's a simple matter to multiply 200 times 9.8 times 50 and then divide by 180. And that's just going to give the number. And the units are going to be kilogram meter squared per second squared. So kilogram meter squared per second squared. And if you think about it for a while or double check it, that is equivalent to the work in joules, or the energy in joules, because a kilogram meter squared per second squared is the same as a joule. And so we're going to have joules per second as a unit of power, and 1 joule per second is also the same as a watt. So when we plug in those numbers there, we do get the units that we expect. So we're not just evaluating, we're taking a step forward to our assessment by checking the units are what we expect in watts. So now we just need to multiply 200 times 9.8 times 50 and divide by 180. So plugging in the numbers, we find that the power is 544 watts. Okay. So now this is this step here, compute the work and lifting up, and then we need to convert the work to horsepower, and that's just a unit conversion. Is probably located in your book. We can Google it up pretty quickly, and we find that 1 horsepower is equal to 745.7 watts. So to convert the power, which was 544 watts, we would divide by 745.7 watts per horsepower, and that's going to give us a little less than 1 horsepower once we do that. And I'll leave that computation as an exercise for the diligent student. This problem also had a hint in it that it wanted us to discuss the conservation of energy a little bit, and it's a little ambiguous exactly what it wants to say. Let's go ahead and do a very brief review of the conservation of energy. Now, the conservation of energy applies to a system when there's no external forces or there's no work being done. So strictly speaking, there was work being done in lifting the drum. So this is just sort of an aside. And probably talking about the conservation of mechanical energy here. And that just says if you have a system where there's no external forces and no work being done, the initial energy is equal to the final energy, so that the energy is conserved. And a lot of times you can think about the energy of a system as being a combination of the kinetic energy, and a lot of times the symbol U is given to the potential energy. So the initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy. And many times when you're dealing with a point mass, the kinetic energy can be understood as 1/2 mv squared, so it's mv initial squared, and the final kinetic energy would then be 1/2 mv final squared. And this is only true if you have a point mass. If you have an object like a sphere or a rod that might be spinning, it can also have an internal kinetic energy from the rotation that's happening. So there's another term that you need to add to account for the internal kinetic energy. But this is the formula as it applies to point masses. And then also, many times when you're talking about gravitational potential energy, this would be mg h initial, and this would be mg h final. But this only applies when all of your potential energy is gravitational potential energy near the surface of the Earth, where the potential energy can be expressed as mgh. There are other cases where your potential energy, say from compressing a spring, might look more like 1/2 kx final, where the k is a x final squared, where the k is a spring constant, and there are different kinds of potential energy that come in depending on the problem that you have. So the idea of conservation of energy, or conservation of mechanical energy here, is that the total amount of energy, kinetic plus potential, is conserved in the system, but you can trade back and forth between different kinds of energy. For example, if you just suppose you have the ground here and you have a ball at some height, you might have V initial equals 0, and you might have it falling through some height is the initial height, H final equals 0. So you start with no kinetic energy and some potential energy in terms of the mg H initial, and so this potential energy gets converted to kinetic energy on the way down. The total energy is conserved, so you can use this idea to compute the final velocity when it hits the ground, just from knowing that all the kinetic energy came from the initial potential energy being converted to kinetic energy on the way down. So that's a convenient way to solve a lot of different classes of problems.